Hello, my name is Revan Joshi from Riverside High School. For my GIS final project, I created a way to visualize and predict future collisions between satellites and space debris. Many technologies of the modern world require interaction with satellites in order to function, such as GPS, weather services, astronomical observation, and communications. By 2025, humanity is projected to deploy nearly 1,100 satellites annually, and this figure is only going to rise as private companies further the deployment of satellite networks such as Starlink, Intelsat, and Iridium. As the number of satellites in orbit increases, collisions between satellites and space debris will inevitably become more frequent. Currently, there are hundreds of millions of space debris fragments circling the Earth at speeds faster than a bullet. When these fragments collide with satellites or other space debris fragments, they don't slow down and fall back to Earth. Instead, the newly formed fragments from the collisions continue to orbit the Earth at even faster speeds due to the law of conservation of momentum. These new fragments can now collide with even more satellites, creating a collision cascade. This phenomenon is called Kessler syndrome, and if not dealt with soon, could be the end of humanity's possibility of a future in space. The first step of this project was to create a 3D scene that allows for satellites and other orbiting bodies to be plotted in real time. Since a backend platform for the future algorithms I would create was needed, I used the ArcGIS JavaScript API to render my scene. This looks just like a regular ArcGIS web scene, but allows for data to be interacted with using the JavaScript programming language. I also used a Python web framework called Flask, so the website could be deployed and embedded into the story map you're looking at right now. The next step is acquiring and plotting the data I would use to train the machine learning algorithm used to predict collisions. All objects that orbit Earth have their position and velocity encoded in a two-line element set, also called TLE. TLE data is routinely updated by the North American Aerospace Defense Command and can be accessed for free on a website called SpaceTrack. As you can see from this example TLE set, it is very difficult for a human to interpret, and a mathematical model is needed to derive the object's position. To do this, I used the simplified general perturbations 4 propagator to arrive at a position that I could convert to a geodetic using simple trigonometric transformations. These coordinates could then be plotted in my ArcGIS JavaScript scene. One downside associated with TLE data is its innate inaccuracy. The position given by a TLE set at any given time is simply a prediction of where the orbiting object might be. To give it credit, the SGP4 model equations factor in many different variables, including the gravitational influence of the Earth, Moon, and Sun, the slight atmospheric drag present near Earth, and the eccentricity of the orbit. This, however, can never be 100% accurate and thus could cause many false positives and negatives when attempting to predict orbital collisions. The scene here shows the real-time position of the International Space Station using the latest TLE set at the time of recording. All the other data points are TLE sets captured previously throughout the month. As you can see, even though all the data points are for the same orbiting object, small errors in calculation over time create massive errors as the time gets further away from the measurement point. To predict the error in any given TLE set, I created a machine learning algorithm that generates a probability distribution of where an orbiting object may truly be. This works similarly to electron clouds in quantum mechanics, as this algorithm shows the probability of where an object may be at any given time using the measured error from past TLE sets. Lastly, I created a JavaScript function that animates the position of the orbiting objects in real time. Now that we know the accuracy of the TLE data at any given time, I created a second algorithm that predicts the collision probability over a 3-hour orbital period. This last scene shows satellites and space debris that are considered to be well tracked. When they are clicked, a pop-up shows the object's name, NORAD ID, and collision probability over the next 3 hours. I limited the prediction period to 3 hours because longer durations become computationally expensive and the accuracy of the prediction drops the further away it gets. Above the pop-up lies a button that, when clicked, shows the actual orbital path of the object. For most orbiting objects, the collision probability is very low. This is because even though the scene shows hundreds of data points that appear to be close to each other, there are hundreds of miles separating the different objects. On top of this, the prediction period is only 3 hours, so the likelihood of any immediate collision is expected to be very low. The real-life application of this project can be generalized to 4 different use cases. Firstly, future missions centered around space debris removal can use these algorithms to identify the most problematic space debris fragments that should be removed first. Next, this can be used to generate new orbital paths for future satellites that have the least interference with other satellites and space debris fragments. Next, when collisions inevitably occur, industry sectors that will likely suffer a loss of services will be able to prepare before the collision event. Lastly, the TLE error prediction algorithm can be used to correct inaccuracies of TLE data in real time, allowing for a far more accurate prediction of where any orbiting object truly is. Thank you all for listening to my presentation.